is a CRCS postdoctoral fellow at Harvard University. She earned her PhD degree from the Department of Computer Science and Automation (CSA) at Indian Institute of Science. She has been awarded the Best Thesis Prize by the Indian Academy of Engineering 2021, Best Thesis Award by the Department of CSA-ISc, a Google PhD Fellowship, and a GHCI Scholarship. She has been recognized as a rising star in STOC 2021 and in the Trustworthy ML Seminar Series for her contribution to algorithms for fair decision making. Her broad areas of interest include algorithmic game theory, optimization, and machine learning. She has worked on a wide range of problems, including health intervention planning, fair resource allocation, multi armed bandits, online crowdsourcing, dynamic pricing in transportation, and ride sharing. At the end of today's talk, there will be a short Q&A session where the participants can raise their hand and ask their desired questions. Now I would like to hand over to Dr. Arpita.
Thank you so much. Thank you so much for the wonderful introduction, and it's a pleasure to be a part of this seminar series today. Hello everyone. I'm Arpita. I am a postdoctoral fellow at Harvard working with Professor Milind Tambe, and I completed my PhD from Indian Institute of Science under the supervision of Professor Narahari Yadati and Professor Siddharth Burman. Today I'm going to talk about my research on decision intelligence for health intervention planning. Now, before heading to the problem formulation, here's a big picture of my research areas. So my work lies in this area called algorithmic decision making for social impact, where I design and develop algorithmic solutions aiming towards fairness, resource limitations, robustness, and sustainability. During my PhD, I investigated fairness concerns arising in the context of allocation, recommendation, and classification problems. My current research includes planning under uncertainty and limited resources. In particular, I collaborate with several nonprofits to provide decision support for public healthcare programs. So these are some of my projects that revolve around maternal and neonatal health. Maternal health care refers to the health of a woman during their pregnancy, childbirth, and postnatal period. And neonatal health care refers to health of a newborn, typically within the first 28 days after a child is born. Now, the first project that I'm involved in is with an India-based nonprofit called Arman, where the aim is to spread life-saving information through voice messages. The second project is with a Boston-based nonprofit called the Family Van, where the goal is to schedule health vans to make healthcare more accessible to low-income families and underrepresented communities. And the third project is in collaboration with Harvard Public Health School, and it's about estimating newborns' risk of missing their required vaccination and then using those estimates for scheduling vaccination drives. So all these projects lead to several challenging and complex problems in the context of healthcare planning. Importantly, maternal and neonatal health has been the focus among the 8 Millennium Development Goals that are adopted by all United Nations member states. Out of these 8 goals, 2 of them focus on reducing child mortality and improving maternal health. And this is crucial because many countries, including India, have a very high maternal mortality ratio. So while United Nations target is to ensure less than 70 maternal deaths per 100,000 live births, India's maternal mortality ratio is still more than 100, and this requires attention. So today, I'll be talking about our work, which is in collaboration with Arman, towards improving maternal and neonatal well-being. So to recall, maternal health refers to health of a woman during these 3 phases, during their pregnancy, during childbirth, and also in the postnatal period. And maternal health care especially needs critical attention because maternal deaths are unacceptably high in India, especially among low-income communities. And this is mainly due to the lack of obtaining timely information about preventive healthcare. Now, for ensuring timely information, Arman carries out a free call-based program called M-Mitra for spreading preventive care information among pregnant women and new mothers via voice messages. Now, this program is targeted specially for underprivileged and low-income communities in India. Here are some more details about the program. So, this program has reached around 2.5 million women, and each enrolled woman receives around 140 automated voice messages throughout their pregnancy period and even after childbirth. And each of these voice message equips them with critical life-saving healthcare information, which otherwise they don't have access to. And this program provides support for around 80 weeks. Now, the aim is to ensure that the enrolled women listen to most of the information that are sent to them. However, it is observed that the engagement of the beneficiary gradually decreases over time, and this engagement can be actually improved by providing an intervention by, for example, by a personal visit by a healthcare worker, where they explain that it's important to listen to these voice messages and important to keep engaging with the program. Now, the goal is to systematically choose a set of beneficiaries for interventions. But there are these 4 key challenges in this problem. Number 1 is uncertainty. That is, post-intervention improvements in engagements are uncertain. By that, what I mean is, if a healthcare worker visits a particular woman, then it's not obvious that to what extent their engagement would increase or whether the engagement would remain the same. So it can sometimes improve, sometimes it may not. So the improvements are stochastic. The second problem is limited resources. That is, the number of healthcare workers are way less than the total number of enrolled women in this program. So it's important to understand that each healthcare worker requires dedicated time and effort for providing intervention to this to the woman. So we need to only allocate, like we can only give interventions to a very small subset of women. So this ends up being like a resource limitation constraint. The third problem is that the engagement dynamics of the beneficiaries, they are unknown a priori. So when we start, we don't know how they would act to interventions, or if no interventions are provided, then to what extent their engagement would drop. And number 4 is that this is a sequential decision-making problem. So the actions or the intervention decisions that are taken at a particular time step, it has an impact on all the beneficiaries in the future time steps. So we need to carefully and systematically choose a cohort of women to be intervened at every time step. Now, considering all these challenges and after several iterations of modeling and data collection, we formalize this problem as a restless multi-arm bandits problem. And this brings us to the first set of results that I'm going to share with you today. This is joint work with Gaurav, Pradeep, and Milind. In this work, we model healthcare intervention planning as a restless multi-arm bandits problem and develop an adaptive learning policy for scheduling interventions. Now, let's look at what is a restless multi-arm bandits problem. So in this problem, we are given a set of arms, say there are n number of arms, and each arm is associated with a Markov decision process. So a Markov decision process has a set of states. So each arm has a set of states, and then there is a set of actions. And in our case, it's like the actions are whether somebody is intervened or not intervened. Now, when an arm is intervened or not intervened, in any case, they would actually change their state. They have a probability of changing their state, going from one state to another. And this is defined by the transition probabilities. And then there is also a reward function associated, which tells you that if you land up in this particular state, because this state shows good engagement value, you have like higher reward. So there is a reward function associated with each state. And because this is a budget constraint problem, a budget is given to us, which is M. And so these all are the given input to the problem. Now, what happens in a restless multi-arm bandits framework? It's a planning problem. It's not a learning problem. It's just a planning problem where at each step T, each time step T, a set of M arms, which is the budget, a set of M arms are selected out of all N arms using a computed policy. Now, what is a policy? A policy is a mapping that takes a state profile. So it looks at the current state of every beneficiary and it outputs an action profile where it says that whether or not to intervene on all the arms. And then because of the budget constraint, we know that the total number of active interventions in this mapping has to be limited by capital M. Now, once these actions or interventions are taken on each of the arms transition from one state to another depending on what action has been taken on them, and then we observe a reward. Now, these observations are then used to update the policy. So the problem is to find a policy that maximizes the total expected reward such that at each time step T, the total number of active interventions taken where A, I, T will be 1. So such active interventions are only given to at most M arms. However, solving this problem optimally is P space hard. So it's computationally a very difficult problem to solve. But the good news is that there exists Lagrangian relaxation version of this problem where Whittle in its seminal paper has shown that if you decouple the problem and then compute some values which are called indices for each arm at each state, then that index itself says a lot about how do you actually schedule. So what you do is after you compute these indices, you select the top M arms according to this index values. And this has been shown to be optimal under a technical criterion called indexability. But before that, let's try to understand what these indices are. So this index is the minimum subsidy that is required to make action 0, that is no intervention action, as valuable as the action 1. So once you have this number, you know that what is the and if you choose like those arms which have high value of this index, you're basically saying that you are trying to maximize the total benefit that you get after giving an intervention. And note that all of this setup assumes that the transition probabilities and everything is known. So it's just a planning problem. Like how do you compute a policy if you know the transition probabilities, if you know reward, if you know everything. Now let's get to the model that how we model healthcare intervention planning in restless bandits. So what we assume is all our beneficiaries are like arms, and each beneficiary can be in one of these 3 states at any point of time. So these 3 states are self-motivated state, persuadable state, and lost cause. So what is self-motivated state? In the state, the beneficiary picks up almost all the calls and listens to them almost completely, thus showing high engagement. Now, naturally, there is not much necessity of providing interventions in this particular state. The second state is the persuadable state. In this state, the beneficiary engages less frequently, but there is a possibility of increasing engagement when an intervention is given to them. It is important to identify beneficiaries who have reached this particular state and provide proper intervention so that you can send them back or keep them engaged. The third state is the lost cause state, and typically the extent of engagement here is very low, and there's a high chance that the engagement remains low regardless of any intervention given. Now, once a beneficiary reaches a lost cause state, they're likely to just remain disengaged in the near future. So, given this, our problem is to select a subset of M beneficiaries at every time step to maximize the total benefit of intervention. Now, if these probabilities were given, we could have computed Whittle index directly and then implemented like a restless bandit solution for this problem. However, it is not the case that we know the transition probabilities beforehand for all the arms. So we need to eventually learn and also act at the same time. And that's the problem that we tackle, that what do we do if the transition probabilities are unknown a priori? We propose a solution that dynamically learns how to intervene and when to intervene with the assumption that the transition probabilities are unknown a priori. So our algorithm actually uses a queue update, and this is a particular way to update the value of a particular state at a given action for each arm. So we use a queue update, and then we use those updates to somehow learn the Whittle indices. So instead of computing Whittle index, which we cannot do because we don't know the Q values, we try to learn the Whittle index instead. And we show that under mild assumptions, the algorithm that we propose actually converges to optimal policy asymptotically. Okay, so now let's get into the experimental results. So what we do is we simulate the behavior of 5,000 beneficiaries, and we assume that there are 100 healthcare workers. Now, every week, a healthcare worker visits only a subset of, say, 10 beneficiaries. In that scenario, we use our algorithm and see that the reward obtained, accumulated, is higher than the other baselines. And this basically means that there are more beneficiaries who are in the good states, like either in the self-motivated or pursuable state when this algorithm was kind of used. And we compared it against two other baselines. So one of this baseline, the red one, is called a greedy algorithm. And this algorithm selects those arms who tops according to accumulated benefit at their current state. And we see that this is not a good method when we have to like learn plus act. Another baseline that we use is just a random baseline that selects a set of M arms uniformly at random. Again, if we are trying to maximize reward, random is not the best thing that we could do. The third is an interesting baseline, which is called myopic. And this is also an intuitive way in which this intervention planning can be thought of, is that the arms who have very low engagement history, try to intervene them and improve their engagement. However, what we realized is myopic does not really work because of the fact that there is a lost cause state involved in the Markov decision process. So what basically happens is there are a lot of arms who have very low engagement history. However, even if they are intervened again and again, they are not going to increase their engagement with the program. So it's better to not intervene them and rather intervene people who actually would improve. So finding those and learning about those arms is important, and that's what we do here. And these are all simulation that I'm talking about at this point. And on the right side, if you see, what we do is we carefully simulate the environment in a way so that after 28 weeks, which is around like 7 months, all the beneficiaries kind of change their behavior, by which I mean that the transition probabilities of all the arms will change randomly. Now, once this is done, the previously learned values, Q values are all they are stale, so they have all changed. So what we observe that our algorithm is able to adaptively again learn the new transition probabilities and take the best actions in those scenarios. However, the other algorithms which are not learning but just accumulating or estimating some other values, they kind of suffer in the case that you have behavioral change. So overall, what we show is our algorithm actually outperforms all existing methods. In summary, we provide an algorithm to learn how to intervene in the scenario where transition probabilities are unknown. Also, we show that under mild assumptions, our method actually converges to optimal policy asymptotically. And we evaluate our algorithm on a few well-studied RMAP examples. And then also we evaluate it on the simulation environment, which is in the context of maternal health care. Okay, so with that, that's the end of the previous paper that I was talking about. Next, I will talk about learning policies for multi-action restless bandits. And this is joint work with Jackson, Sanket, and Milind. So in this work, we investigate multi-action restless bandits. So like before, we assume that there are n women or patients given to us, and instead of two actions, previously we just assumed there are two actions, no intervention and intervention. Now let's say there are multiple actions that either a healthcare worker can choose to personally go and visit for providing an intervention, or they can simply call them and try to convince them to keep engaging with the program, or they might just try to nudge them by sending some text message. So each of these different actions have different costs or requires different effort from the healthcare worker. And also each of these action have different effect on the patients after intervention. So yeah, so what we would do here is we would try to, instead of trying to put one budget for the number of arms to pull, now that we have cost associated with different actions, what we want is every time we want the total cost to be within some given budget. And what we observe is every time a particular arm or a patient might have improved their engagement or might have not improved their engagement depending on the interventions that are provided to them. So if we have those observations and if we keep learning about those more and more, then at time t, the thing is how can we design a system that is going to output what actions to be taken on each of these arms. And then no action is also included in the set of actions. Now recall that RMAP problem is an extremely hard problem to solve even for two actions. So we end up in that computational hardness problem even here. However, the previous algorithm that I mentioned works only for two actions. So for multiple actions, we have to do something more smart. And for that, we developed two algorithms. The first one is called multi-action index-based Q-learning algorithm. And this algorithm, we show that it converges asymptotically to the optimal policy, but it requires one particular assumption, which is called ordered intervention. That is, we assume that the actions are such that there is always an action which requires very less cost, but it also have lower effectiveness. So it has lower probability of converting somebody from persuadable state to self-motivated. And then yeah, so we have like different actions, and each of these actions have like an ordering of their costs and effectiveness. So with that assumption, our algorithm is actually asymptotically optimal. But the second algorithm actually captures the fact that you may not have such cost structures. And in that case, you still need to have an algorithm that gives you something, an efficient solution. So what we propose here is an algorithm that does not require any assumptions. However, for two actions, this algorithm would have like a theoretical convergence guarantee. And without like when we are talking about multi-actions, we do not have any convergence guarantee for LPQL. However, in all our experiments, we have seen that this particular algorithm outperforms all other algorithms, especially because this does not need like structural assumptions. So whenever there are no structures in the problem, LPQL turns out to be really good. Now I'll one by one talk about each of this algorithm. So the first one is about computing an index. And the intuition behind this index is it's a long-term value of assigning one more unit of resource. So by one more unit of resource, I mean that if there are like 3 actions, one more unit of resource is the next better action. So if we want to find that index, we need to introduce a term called lambda that amplifies the cost associated with each action. So this is the typical Q value for a particular MDP. And now we are converting this Q value into a different expression where we have amplified the cost associated with an action, which is, so the cost for action J is Cj. And then we have used an additional parameter with this to say that this is the new reward. Now, after doing that, we have 2 goals. Number 1 is to find a value of this lambda such that it acts as a subsidy for taking a less effective action. And once we find that lambda star, we also need to learn the Q values along with that. So this Q values and lambda both are kind of unknown a priori. So we need to like eventually learn and figure out what these values are. So we do something similar to previous algorithm, but not exactly same, because here we need to update both of them in 2 different time scales. So for updating Q values, we have to learn, like we have to update Q values in a faster rate, and we need to update the lambdas in a much slower rate because we need to accumulate enough Q values to actually give like a good index value. And then we show that this algorithm actually converges well when there is indexability assumption that holds, and also when there is this even cost distribution structure. Okay, so now I'll go to the next algorithm. So when there is no cost structure, and even if we don't want to rely on indexability, let's think about going back to the basics, and we look at the Lagrangian relaxation with multiple actions, which looks like this. Now, after we have this particular problem, now the first term of the objective is actually a linear term with respect to lambda, and the second term is a piecewise linear and convex function of lambda. So we make use of these properties, and then we know that we can now estimate the curve V by approximating Q values using a possible set of lambda values, because this entire function is kind of convex. What we show is that doing that, this particular algorithm converges to optimal Lagrange policy asymptotically for binary actions. And as lambda, number of lambda points that we use, that if that is considered to be infinity, then also this algorithm is optimal. However, that's not practical. Now, this algorithm generalizes the MAIQL algorithm, especially because there is no structural assumption required. So it is applied for a more general class of this RMAP problems. In our experiments, we see that both LPQL and MAQL performs better than some of the existing variations of 2-action solutions. And we also additionally see that LPQL performs better than index-based policies for non-indexable domains, which is detailed more in the paper. Okay, so overall, this is the This is how we positioned these two papers, is that this is the space of RMAP problems, and there has been a lot of results on when we know the transition probabilities, and we have binary action versus we have more than two actions. So there has been a lot of results in this space. However, dealing with unknown transition probabilities has its own challenge, and then both of our work look at binary actions and multi actions and try to give a better solution in this space. Okay, so that brings us to the end of the learning aspect of restless bandits planning problem. Now, what we observed is that it's not enough to always learn, and learning is one aspect, but then there can be situations where you have enough data to estimate transition probabilities, and you might actually just be able to use Whittle index. However, there are other challenges. So the one of the challenges that we tackle is that the set of arms may not be stationary. They can be incoming set of arms and outgoing set of arms when we are talking about a healthcare program. For example, again, let's take the example of health intervention planning, where there are new beneficiaries who enrolls every week, and then there are some beneficiaries whose program has ended and they are leaving. So if there are this streaming arms in the bandits problem, then it makes it difficult to directly use Whittle index and solve this problem, because the set of arms is not stationary. So we tackle this issue in this particular paper. And this gives us interesting insights on what do we do when we have when all the arms are not always available. The second thing that we realized is that if we are trying to estimate transition probabilities from the given set of observed data points, often these estimates are not very accurate, and they can lie within a particular range of within a particular interval range, but it's not like the perfect estimate that we observe. So in those cases, our algorithm should be robust towards these perturbations in estimates, and that leads to a very interesting problem formulation of RMAP by itself. So we call that problem robust restless bandits, and this is another line of work where we have which we have recently published. The third one, and I'll deep dive into the third part in a few other slides, but just to give you a high level idea of what's going on, is that we realize that most of the RMAP literature have only considered whom to intervene, like which arms to choose and whom to intervene and at what point they should be intervened. However, there is another aspect that after you choose a set of arms for intervention, it needs to be allocated to the set of workers, and then whenever there are multiple workers, each worker would have their own cost, each worker would have their own budget, and then you have to maintain all those constraints, and then also plan on the arms. So putting all this together makes it like a really important and interesting problem. And I will spend some time, like the next 10 minutes, talking about these results. Okay, so what we do, we introduce this new RMAP problem called multi-worker restless multi-arm bandits. So here at each time step T, we allocate a subset of arms to each worker. So previously we were just interested in finding which M arms to select. Now we need to select and allocate a subset of arm for each worker. And what we additionally assume that instead of the global overall budget B, now each worker has their own budget, and each worker may have different costs for intervening different arms, and they also have different effectiveness in the sense that a particular worker may help improving engagement for a particular arm, but for another worker, the engagement may not increase. So there are differences in the efficiency of a particular worker when they are intervening on a particular kind of patients. So after this allocation is done, this is again similar to what previously happened, that each arm, depending on who has intervened them, changes to goes to a new state, and we observe a certain reward. Now, the additional thing here is, because there are multiple workers, what we want is at each time step, the difference between the total cost incurred by any pair of worker is restricted by a fixed number. And this is required because if we don't do this, there will be no load balancing among the workers, and a worker who is more effective or more efficient in terms of improving engagement, they would get a lot of workload versus others who won't like really get so much of allocation. So what we want to, so this is the problem formulation that we are working with, where we are trying to maximize the total expected reward subject to a budget constraint per worker, and each arm should be intervened by at most one worker at any point of time. Also, there is a fairness constraint that balances the load across all the workers, and then there are integrality constraints, that is like the interventions are integral values. Now, how do we solve this big problem? So the first step we do is to identify subproblems, and we decompose a combinatorial problem into n cross m subproblems, where m is the number of health workers and n is the total number of arms. And now, after we decompose this into subproblems, we have, you can imagine there, each of this problem looks like an MDP with only two actions. What happens when a particular worker intervenes, and what happens if they don't intervene? So we are back to the two actions state if we are looking at a subproblem, and then we can compute Whittle index for the subproblem. However, only computing Whittle index is not enough, because Whittle index just captures the charge that makes the value of intervention equal to the value of not intervening. It do not take into account that in future steps, some other healthcare worker might intervene, and that dependency is decoupled when we are looking at the decomposed values. So in step 2, we adjust these indices to capture the inter-worker dependency. And the way we do this adjustment is by saying that what is the minimum charge required to make sure that this worker is as effective as any other worker if they intervene in the future. And we show that using this adjusted indices, if we order the worker based on this indices and then allocate arms in a way that every worker gets to choose the arm who will be most benefited by giving an intervention with this worker. If we keep doing that and do it in a way where each worker meets its budget, so we end the round robin allocation as and when the budget is met for a particular worker, we show that this process would have in certain cases, it would always make sure that the allocation is fair. And for computational improvements, additionally we prove a few theorems which say that if all the costs of all the workers are equal, and if their intervention effect or the transition probabilities are all equal, then the underlying indices that we are computing, they are also equal for every worker. And this theorem is like an intuitive one, that if all the workers are same, basically we are saying that they come from the same cohort and they are like either intervention or not intervention, so they don't have different costs. The second theorem is more interesting, which says that if the transition probabilities are same, so the intervention effect is same. However, the costs of the workers are different. So the cost of intervention of a particular worker for a particular arm may be kind of different. Then at least this, at least what we know is that the indices would be inversely proportional to the cost. So you can just compute this indices for one worker and use this particular expression to update the indices for all other workers. So those two theorems helps in further improvements on the index computation part. In our experiments, we see that the algorithm that we propose, it has an improvement in fairness, which is load balancing, with the improvement is around like 3 times more than an algorithm that just tries to only maximize reward. And while we achieve fairness, the reduction in reward is only around like 6% from the optimal. And one thing to note is you cannot really solve this problem optimally for a larger number of arms, because I mean, you can imagine that you can use this big framework as like one giant Markov decision process and then solve that big Markov decision process. This is of course possible, and we compare the results for small number of arms, but as and when we increase the number of arms, it is the optimal is impossible to like. It takes up a lot of memory. In terms of execution time, we show that our algorithm is much faster compared to the existing state-of-the-art algorithms. Great. So in this work, we basically introduce this multi-worker restless multi-arm-bandits problem with fairness and budget constraints. We propose an approach for solving this fair multi-worker restless multi-arm-bandits problem. We show that the computation can be made much faster when this problem has some cost structures. And also that we evaluate our approach on multiple RMAP instances and show that it produces fair solution with marginal reduction in reward accumulated. So with this, this brings us to the end of this talk. So I will end by sharing some of my experience and takeaways in working in the space of decision making and for social impact. So the first point is that the societal problems are really hard to solve. So we have to choose our abstraction wisely, and we need to talk to experts and use like do a lot of iteration of what is the best abstraction to model this particular problem. The second point is that it's good to build expertise on a wide range of computer science techniques because you would then know what can be used and when, like which technique can be used for solving what kind of problems. And the third is when we are talking about real world deployment, there is a lot of concerns and issues related to fairness. There are sustainability requirement, and there's also robustness of the system that we need to be mindful of. With that, I will end my talk by saying that it's an absolutely interesting space to really work towards problem that has a potential impact and that is going to change life of like millions of people. And I encourage more people to like join this effort and try to think about how to take their algorithms from just being like a theoretical concept or a foundation to actual real world deployment. So thank you everybody for your attention.
Thank you, Dr. Ashok, for the informative talk. And with this, I will also invite everyone to ask their questions. If any, you can raise them, your hands, and we can proceed to Q&A session. Looks like there aren't any. So, Arpita, in fact, I would like to ask one question regarding the reward of your whole algorithm. So, if we want to explain how the reward is, and it's based on it's what it is based on, a few key points, physical entities on that reward is based on. How will you attribute that reward? What will you attribute that reward? So,
Yeah, that's a very interesting question. So actually, there are many ways to estimate the reward, but the way that we do in most of this work is we try to put like higher numbers to those states which are more desirable. So ideally, if you want to capture the reward in terms of engagement, you can do that by using like the estimated total engagement when somebody is like really active. They are like listening to every call. So that can be estimated, but we don't do that basically because our estimates are itself like not very accurate. So instead, what we do is we put like a reward of 1 or 2, which is like a positive number for states which are good states. And then there are bad states, for example, the lost cause state, where we say that there's a low reward. So you don't really end up landing in that state. And if you do, then your algorithm incurs some penalty or costs. So that's how we put rewards in all of these work. But the model is actually more general. Like you can actually use other estimates for reward.
Oh, okay. Yeah. Yeah, thanks. Thanks. I understood that part. Uh, and any other questions on this?
Hi Arpita, this is Prachi. I wanted to ask like this work is very interesting, and then it can be extended to other fields also, like this call center scenario where there is a customer and an agent, and nowadays there is a lot of need of these call centers because of COVID and all came up. So uh, like this industry, like people are interested that the agents should be more like engaging to the customer. So uh, can we use the same scenario like to identify like how the agent behaving, and then we can identify which agents are not doing well with the customer, and then we can train them or maybe replace them, something like that.
Right. Do you see the requirement of Markov decision process anywhere here? Like, I totally agree that this is an important problem, and this is also a learning problem. I'm just wondering whether this is a stochastic bandits problem or a restless bandits problem, in the sense that if you just want to learn the quality of or whether or not a particular agent, call center agent, is doing good, and if not, then you want to give them some kind of training.
Mm-hmm.
That so you are saying that each agent is an arm,
Mm-hmm.
and then each agent has a particular state of learning. This is very interesting. So yeah, this requires more thought, but I guess you can capture this as a Markov decision process if you know that the agent's behavior changes according to Markov decision, and whenever there's a training, they kind of improves. But do you think that if there is no training, then if they are not, let's say they have been trained, do they keep staying in the same state, or they eventually again degrade until the next training happens?
Those details I'm not sure, but yeah, means the problem is that there are managers for these agents, so they have to like listen to the call to understand whether the agent did good or not, and they will give some rating. So there are millions of calls, and they pick some like cherry pick some calls, and
Hmm.
based on that only they will decide. So the like uh, if in order to like automate the process, what
Hmm.
the industry is doing is that handling these calls and passing to some algorithm like natural language processing or something to
Hmm.
identify the emotion of the customer, and then that will be like some positive emotion, then it is like the agent did good. If that is a negative emotion, then agent did bad, like that.
Right.
So the again the like you had the workers as like limited, here
Hmm.
the managers will be limited, so it's
I
like that.
see. I see. Yeah, maybe there is a version in which you first estimate some values and then use those estimations. So these are probabilities. Like when you say that this is like the natural language processing is estimating something, they are just putting some probabilities. So maybe you can convert those probabilities into saying that they are some kind of values or rewards,
Rewards. Yeah.
and yeah, maybe this can be used. But of course, I think it needs an association with some learning technique, like some machine learning framework to
Mm.
even speech processing, something.
Yeah, yeah, that is correct. Yeah.
Yeah, but interesting. Thank you. Thank you very much.
Yeah, thanks.
Okay, any more questions?
So one question from my side is, the people that I'm seeing are everybody from IISc?
Yeah, actually, a few were there. Uh,
Okay,
they were not I guess.
I
Yeah,
see. So
not.
I see two guests.
Yeah.
I'm just curious if you want to unmute yourself and just say where you're from and what are you working on. I'm looking at Anandi and Dhawal.
Oh, she is.
Yeah, I am from IISc
Oh,
and yeah, I'm the branch counselor of IISc student branch.
I
Yeah,
see.
thank you very much. And yeah,
Sure. Which department are you in?
EC department.
Okay.
Yeah,
Okay, thank you. Nice to
yeah, yeah.
meet you. And Dhawal?
Uh, Hi Arpita, it's Dhaval here. Can you hear me?
Yes, I
Yeah.
can hear you.
Yeah, I am a student in the Department of Management Studies IISc, and I'm working on the development of algorithms which can be used in the manufacturing industry in the semiconductor manufacturing area.
Oh, very interesting.
So
Thank you.
it
Thanks
was
for
nice
joining.
experience to attend this talk, and basically my background is in the mechanical engineering, and I'm working in the area of algorithm development, and I'm using several meta heuristics to do the scheduling activities. So it was a wonderful experience to attend your this talk.
Oh, that's great to know. Thank you.
Thanks, Dhaval. I guess we don't have any more questions, and we are on time nearing towards the end time. So, Kunal, if you have anything else that you want to share,
No, it was a really informative talk, and yeah, the mark of Christian process.
Kunal,
I
you
could
just
appreciate it because I'm from a mathematics background. It was a very nice insight. I got to know about the candid problems. I look forward to get into it.
It's great to hear that. Thank you.
Yeah, I would like to add on something. I would like to thank our speaker, Dr. Arpita Biswas, for interesting and useful talk on decision intelligence for health intervention planning, especially healthcare for women before, during, and after pregnancy, and also healthcare of newborns and details on Arman project, especially for low income group. I request everyone to give a big round of applause to Dr. Arpita. And our thanks goes to the Exicom team of IEEE-IISc Computer and Computational Intelligence Joint Society chapter in association with IEEE-IISc HKN for successfully hosting this webinar. I would like to thank Professor Srinivas for his continuous support and encouragement. On behalf of IEEE-IISc student branch, we are also happy to issue appreciation certificate for previous entire Excom CSCIS team, and we would like to thank all the participants for making this event a huge success. Thank you so much, Dr. Arpita Biswas, for a wonderful talk.
Thank you. Thank you for attending. Thank you for the interesting questions.
Yes.
Okay. Bye.
Bye bye.
thanks. Thank you.